Welcome to the TUM AI lecture series. It's my great pleasure to introduce today's speaker. We have another really well-known speaker with us today. This is Bernt Schiele. He's professor at the University of Saarland, and he's also director of the Max Planck Institute for Informatics in Saarbrücken. Actually, since 2010, he's very well known in the field of computer vision and beyond, in machine learning as well. He's had a long career. He's been many places. He studied computer science in Karlsruhe, and then he went to France and got his master thesis in Grenoble, and also a French diploma. He worked in a variety of fields, also in multimodal human-computer interfaces. He was at CMU. He was as I said, many places. He got his PhD in Grenoble as well in '97 with Jim Crowley, and that was in computer vision. And he's been a postdoc, a researcher, and visiting assistant professor at MIT with Alex Pentland. And he's from 1999 to 2004. He was assistant professor at ETH Zurich. And then he moved on to Darmstadt from 2004 to 2010, a full professor in Darmstadt. And since 2010, he's in Saarbrücken. And today he'll be speaking about neuroexplicit modeling for more interpretability and performance in computer vision. It's my great pleasure to have you here. The floor is yours.
Yeah, thanks, Daniel. Thanks very much for the invitation and the introduction. It's a pleasure to be here to, give this talk. I would have loved, obviously, to come to Munich. Munich is always worth the trip, obviously. But I have to say, it's also easier to accept these invitations when there's no trip involved. So in that sense, there's pros and cons, as in current times, I'd say, right? So, okay. So what I want to talk about today is, as the title suggests, neuroexplicit modeling, and you're probably asking, what the heck is that, right? And I think let me start by basically giving a bit of a motivation, what I'm thinking, right, and why I'm thinking actually this is interesting as a direction. And actually, there's quite a bit of work in a sense in that space, but I think there is really good reasons that we want to have more work in that space. And I want to talk about 3 explicit examples, maybe 2 depending on time permitting. The one is what we call Convolutional Dynamic Alignment Networks for interpretable classification. The next one is really a combination of Wiener filtering and well as deep learning for image deblurring. That's sort of another paper I want to talk about. And again, time permitting, I'm going to talk about neural body fitting, where we actually combine a simple 3D body model, right, for 3D human pose estimation in order to really reduce the amount of training data. But let me start briefly to introduce what I mean by neuroexplicit modeling. So first of all, there are major issues, and I think there's no disagreement here about sort of deep learning models, right? And one clearly is interpretability, right? We know that deep neural networks are delivering high performance, or in many settings, but it's hard to interpret, what they have really learned and why they're making certain predictions, right? Really understanding what they're relying on to do their predictions. So that's one major issue, I would argue. And that's one of the first paper I'm going to talk about, is really trying to address that part. So another one is generalization, right? So when you start training on a particular data, right, it starts to exploit the respective statistical regularities for the good and the bad, in a sense, right? And it's hard to generalize beyond that kind of setting, right? Sometimes it's called a generalization beyond the IID setting, right, where we don't have training and test data really sort of properly drawn from the exact same distribution. And in real life, this is very often the case, right? If you just have data that actually is drawn from one distribution, you still want to be able to generalize to other distributions, right? And it's because it's just not possible to have data for everything. You want to do this in a sort of in a seamless manner, ideally. And then sort of another part of the problem, obviously, is that currently the most successful models require a lot of data, right? In particular, supervised data. And the question is, can we, or is there ways to reduce sort of the amount of supervision? And I think sort of what I'm calling neuroexplicit models are basically aiming to address all these things. I mean, not maybe simultaneously in the first place, but at least sort of eventually, I think this is something we should consider more. And when I talk about explicit modeling, I'm really thinking about, for example, image deblurring. We know certain, very particular models, like in our case, we're going to use the Wiener deconvolution filters, which is well known, right? It's from the 40s. And can we actually integrate this, I think, as a bottleneck or as an explicit model, as an attritional model, and enhance this with neural network training, right, to really sort of increase performance and generalization abilities. As I said, there will be really three directions I want to explore here. The one is for interpretation, and here we're doing structural constraints. Now it'll become clear what I'm talking about. What I mean by that, explicitly on the network, we're really redesigning the network and training it, anew to really allow, inherent explicit interpretation of the results by design, essentially. The one I also mentioned, right, is this: when we are we able to generalize beyond sort of this classic setting where things are trained on. And here I'm going to talk about is what we call the Deep Wiener Deconvolution, combining Wiener filtering as well as with neural network training. And last but not least, depending again on time, as I said, right, I want to also talk about how we can use 3D modeling like Simple Model to really reduce the amount of required data to really do a better job in that case 3D pose estimation. And just and again, these are just sort of examples of this type of work, right? And I think the one direction you might have heard of is the neurosymbolic models, which really sort of trying to combine symbolic AI methods with neural network training. In a way, this is sort of a special case of what we call neuro-explicit models. So in that sense, you can think of this as really sort of trying to use more traditional classic models that you tend to understand quite well to really integrate them into neural networks and actually then hopefully obtain better neural networks models in this context, in this direction of interpretability, generalization, and require less data. Okay, so let me start with the first example. That's the so-called coordinates, right? Convolutional Dynamic Alignment Networks for Interpretable Classification. And this is work of the Moritz Bürlitz, a PhD student, jointly supervised by Mario and myself, and will be presented at CVPR this year. And again, starting from the motivation of current sort of deep neural networks, right? What most of these models obviously do, they basically are optimized for accuracy, right? You're trying to do on a particular benchmark, improve the accuracy for a particular task at hand. And the models, in a sense, are for the most part black boxes. There has been quite some work on trying to explain what's happening in the neural networks, but most of them are pretty much the majority of them are clearly post hoc, right? You have trained the network, and then post hoc you try to explain what they're doing, right? And here's a classification example for some images here from right here on the left. You see the images, and here's a bunch of explanation methods. They're often called attribution methods, which are trying to attribute, trying to find the pixels that really sort of are mostly contributing to the respective output, right? And the GradCam is a very famous example. And if you look at these images, they're looking actually not totally off, right? If you hear, for example, for the PFOL, right? So basically you're seeing the regions where basically some concentration goes on, or here for the ducks, right? Or here for the kakadu, right? It seems reasonable, but I would argue these are not very satisfying because it's really still sort of very, hard to really, see the details that are really, paid attention to. Other methods like lime and rice are, I would argue, they are much worse visually speaking, and actually also quantitatively, as we'll show later, they're really not that good, even though they're really sort of used by many people to do these things. Gradient methods, these are sort of the other type of methods that people are using for this, post hoc attribution for where the logits, where the scores come from. But these, derivatives kind of or gradient-based methods, they tend also to be not too convincing, I would say, if I look at them sort of here in this space. And again, as we will see later, also quantitatively, they're not as good as what we're trying to propose here. So what we're trying to do is really sort of having a method that actually is by design interpretable, right? We're going to have, and I'll get to this on the next slide, how to basically, have a network that is inherently interpretable by design, but still actually having hopefully some, good accuracy, performant at the end for this neural network. And then just as a peek here into what we're getting. So here are the kind of attributions we're getting. And again, I would argue, right, these are far more detailed. And actually, they're quite convincing, I would argue, right, in terms of what they're looking at in the image. They're really sort of distinctive local features that we would also, as humans, think are the right features to look at to make these respective classification results. Okay, so that's the overall gist of the idea, right? And obviously, right, we want to have a classification model that both sort of does good classification of the individual images, but at the same time gives us attributions. And these attributions, as I said, right, will get through these CUDA networks that I want to talk about here now next. And I'll present them on a relatively high level. I can give a bit more details if you're interested. But the idea here is that it's really a different type of network. That wasn't existing as such before. It's still a network, has multiple layers. We tend to have something like 9 layers or so. They're not that deep actually for even getting still good performance. And there are 2 key design principles that make this actually sort of more interpretable. The first one is what we call dynamic linearity. What does it mean? So at the end, what you're doing, and the second part is actually what we call boundness, in order to really have the network not to sort of attend to a particular part of the image, arbitrarily strong. So what does it mean, dynamic linearity? So if you think about, here you have the output of a particular layer, right, which is sort of a function of the input here of that same layer, right? So that's sort of the output of that layer, right, given the input of that layer. So now here we're having still a linear mapping here, but the key story is that linear mapping itself is non-linearly dependent on the inputs, right? At the end, still, there is a linear mapping that I actually from the first to the second layer and for all the layers. However, the linear mapping itself has a non-linearity in it, which makes it actually sort of, performant enough to really achieve sort of competitive results for data sets. So that's sort of the key thing. It's still linear, but it's a dynamic linear, input-dependent linearity. Right, so now then, the second part is if you look actually at one of those here, these entries here, these are really just dot products because it's just linear mappings. They're just dot products at the end of the day. What you're doing is actually these dot products are also bounded, right? The individual entries, these individual rows in this matrix are bounded, right? They're really sort of normalized to a particular norm, just one for simplicity, which means that also the output, right, how much it actually can be transformed is as well bounded. It's bounded essentially by the inputs, right here, because obviously this has a norm 1, and basically it's bounded by the input norm. So what does that help us? Well, and if you think about sort of this dot product here, in order to maximize the output at the end, right, at the very end, you want to have some very strong logit, right, for a particular class, right? And that logit actually, in order to get the maximum logit output, right, you essentially need to align essentially the row of this matrix with the respective input, right? You really find in order to get the maximum output, you have to align it. That's what we're calling why we're calling them dynamic alignment networks, because they automatically, by finding discriminant features, they're automatically aligning with the inputs, which means then also if this mapping that we're getting is actually really sort of in a way, it's really very representative for the input, right? And that really is by this boundness is actually sort of really enforced. We're doing one thing which I'm not going to talk about here actually as well, is that we're even making this, more we're enforcing this more to be basically aligned by having additional temperature parameter. So if you basically sort of rescale this with another temperature parameter, like making it smaller and smaller, you even more force it to basically align with the inputs. And since we're doing this not for a single layer only, but right, we do this for the entire network, right? Obviously, the CUDA network itself, right, has sort of inherits these properties from these single layers. It's dynamically linear, right? So that really the entire mapping from the input to the output actually is a linear mapping. It is input dependent, which is why we call it dynamic linear, but it also is bounded, right? It cannot be arbitrarily sort of just looking at one feature and just getting the best logit out, but it really has to look at as much possible part of the image in order to really get the maximum output. So that's the boundness which helps here. And what we're showing here as the attribution then later is actually sort of the way you should think about it. This is really now really the linear mapping multiplied with X on a pointwise level, right? And if you now basically take the sum of all those pixels, you get the logit. That's exactly what happens, right? So that's just the sum of the marginal of this image, if you like, right? That's the logit for the particular class. And we have this for each class, which means you have really an attribution for each of the logits, right? How it was generated from the image. That's what the attribution is, and that's really what is used to generate the logits and thus the classification scores eventually. Okay, so yeah, and then as I said, right, the matrix itself that actually we are multiplying here has to align with the discriminant features because of this boundness constraint, obviously. So let me give you some results again, just to make the point, right? And I'm gonna show this qualitatively, but I'm also gonna show this quantitatively to make the point that actually this is not just something that visually seems interesting, but really also in measures actually makes sense. So here are sort of more examples, right? So here you see sort of the attributions, and again, if you remember the attributions I showed earlier, they're far more detailed than what other methods really are delivering, right? And again, right, so if the kind of things you look at here it looks really at the chest of that bird, right, to do this classification of that bird. Here it looks for the ducks, it looks really at the head. So I would really argue these are really quite convincing where you would expect sort of the discriminant features to be, right, to be really sort of used for the respective classification on this data set. So now let me talk about two different ways of doing some quantitative evaluation. And we're using sort of prior work that has been doing this. There's something called the pointing game. What you do, you basically train a network basically on a tile, on a 2x2 or a 3x3 image, right? And by that, if you now know actually here, if you get sort of the plane classification, all the evidence for the plane you know exactly where it comes from, because by design, right, it has to come from the particular quadrant of the image, which means now you can really calculate how much of the evidence of the attribution method actually falls in that part of the image versus the other part of the image where you know there should be no evidence for the plane because there is no evidence for the plane. And you can just do this pointing game and actually evaluate the respective localization of this attribution. That's sort of, there's this so-called localization metric, which really says how localized is the attribution really in that part of that image. And here, if you look actually, so here sort of there's this GradGAM, which is sort of many people use this. It's not bad, right? But this method I'm just talking about is a lot better here, right? It's really sort of quite a bit better. And the gradient methods are actually not that great because at the end they're still having gradients everywhere, right? And it's actually not so clear that they're really sort of giving you the right localization at the end. It's sort of this noisiness of the gradient method that actually is also shown here. Another way of doing this, trying to quantify that really this does something sensical, is what's called the pixel removal metric. What you do is basically you're looking at the attribution method, and then you're taking out the pixels which have the least attribution, right? You basically can be negative attribution even, right? And once you're taking them out one by one, right? So at least sort of the scores should be staying the same. It can be even increasing, right? Because you really take negatively or uncorrelated pixels out of this picture, right? And again, the curve here, right, as you take more and more pixels out. So this is the curve you're getting here with our method, right? So really you're increasing and stay very high actually. And all the other methods sort of sometimes increase, but they really quickly much more decrease, which means they are much more noisy in terms of where the attribution goes. And again, this is just standard methods, right? And we haven't invented them. This is sort of the best we currently have, right, to evaluating this kind of attribution method, but that's sort of give you a gist of an idea, right, how good this method really is also quantitatively. Obviously, at the end of the day, and I haven't really talked about this, the classification performance still matters, right? So we still want to have a performant network. And right now, to be fair, right, we have been evaluating this mostly on Cypher-10 and on Tiny ImageNet. On ImageNet, we have sort of attribution results. There, it doesn't quite work yet 100% in terms of performance, but we're actually working on it. We're going to release something. We have something by now, actually, I'm not going to show here, that is also competitive here. Let me just point out some numbers. So this network here, which we call a small quota network, it has some 8 million parameters or something, right? And ResNet 56 or so has some 25 million parameters, so a lot more parameters actually. You're getting roughly on par, right? So in terms of this performance, it really is reasonably performant, at least as a function of the parameters. If you use a wide ResNet, which has many more parameters, I'm not exactly sure what that is. Also using augmentation, we can also sort of profit from augmentation. So again, you're getting in a similar range of performance. The same holds true for tiny image, right? If you're having a ResNet 110 or so, right, you can again get sort of with what we call an extra large coda network, which now has 62 million parameters, right? So we can again getting really sort of competitive performance, at least on this initial data sets. There was a bit of a struggle right now we had sort of to make this really work on large images, but that's again, I said we're working on this. We have actually 2 new versions. The one will be out soon, even on the web page, right? Another one will be most likely a follow-up submission soon. And as I said, right, so performance-wise, you're still reasonable, right, in this setting. Right, so here, right, as I said, there will be an improved version soon to come, which makes these coda networks more scalable, which is, to be honest, that's sort of a little bit of a downside right now. But still the point I'm trying to make is, right, sort of here, there's this built-in interpretability, right, by this dynamic alignment that we are forcing the network to do, right? And I also would argue, because it's really a linear mapping at the end, it's, it's a faithful decomposition, right? You really have a decomposition of the final logic of the network, right, with respect to input, right? We really know where the network really got its evidence from, right? Exactly, right? It's not a post hoc thing where you do some derivatives and whatnot. It's really, that's exactly what the network is doing. And we, this is by design, basically the property of the network. Okay, there's code available, right? I'm thinking it's anyways recorded and people can just, get this QR code. Okay, so let me move on to, I can also take questions now. I don't know how you do this, or rather at the end, so I'm fine either way. I
think let's take questions at the end.
Sure, no problem. Good.
Thank you.
Okay, so let me talk about the second topic, which is, again, a neuro-explicit model, right, which is potentially even more explicit than the previous one. The previous one really was sort of having specific constraints that we know actually should be good, like having a linear mapping as well as having a boundness. Here is even far more explicit what the model is that we're using here. This is joint work with Stefan Roth, and it's the joint postdoc Jiangxin Dong, right, which is us at the MPI. And it's sort of here, Wiener deconvolution for image deblurring. And we all know what image deblurring is. Just to set up the setting here a bit. The classic case is setting is we have some blurry image. These days you're training a deep neural network, right, to obtain a clear image at the end, right? So that's basically blurry image in, clear image out. That's the idea. However, we know actually that we can actually pretty well model sort of the setting by taking the clear image, then having a blur kernel, basically, really sort of using a convolution with the blur kernel, essentially, right? Add a bit of noise, and that is a very good model actually of the blurry image, right? That's a classic way we're doing this, and it used to be that we're doing sort of maximum posteriori estimations, right, where we really try to leverage this kind of settings. And what we're looking actually here is what is non-blind image deblurring, which means we actually know the kernel. And just to make the point that actually that's an important topic to really look at is, if you look at an example here, a blurry image, right? And if you look sort of standard deep learning methods, they're trying to deblur the image, right? They're not as good, right? If they're blind, so not knowing of the kernel, then when it's non-blind, right, then they really know the kernel actually, or have a good estimation of the kernel. Non-blind methods are really sort of far more performant at the moment still, right, than the blind methods. And ours, again, here just as a preview, right, here actually gets quite a bit better visual performance, and actually also, again, quantitatively we'll be seeing gets quite a bit of better performance. So really, we argue that sort of having these non-blind methods, even though it sounds in the deep learning area, right, sort of we should be able to do everything, right? So these non-blind methods are really having a place, and that's what I'm going to talk about here today. Okay, so now one of the, and I already, said this earlier, right? Sort of there is sort of a very famous method, right? A really old method from the late 40s, right? The Deep Wiener Deconvolution, which basically is a non-blind method, right? Knowing the kernel, it really tries from an input image, basically doing this, Wiener deconvolution to get sort of an estimate of the image, right? And actually in this classic peak signal to noise ratio, right? It gets actually some reasonable number, 27. It's obviously not state of the art these days anymore, but actually it gets something sensical. So now you can think sort of why, and that's a very explicit model. That's a Wiener deconvolution model, right? Really classic sort of linear equations in here that really help us to do this, deblurring. Now we could think of, well, okay, so maybe the Wiener deconvolution is not good enough, right? Why not just adding sort of a bit of image reconstruction network afterwards, right? Actually, that improves whatever the Wiener deconvolution was not able to do. Think about some residual fitting, right? And sure enough, actually, you get some close to 3 points here on the scale. And again, it's a logarithmic scale. That's kind of pretty, quite a bit actually, right, here to do this. Then once you start thinking about this, why not actually adapting the inputs representation for the Wiener deconvolution? At this point, it becomes approximate what this model does, because now you actually have a nonlinear, transformation of the input, right? At that point, it doesn't really is a proper Wiener deconvolution anymore in the image space where you have the kernel, but at least sort of in the feature space, it's still, reasonable to assume this is good. And again, if you learn this end to end, what we do, you can still apply this, right? So here we get a bit approximate, that's for sure, but still actually it does help in performance. Actually here we're getting, and that's even more performance we're getting some 4 points in this scale. And we can get actually can go one step further, right? Actually to do really sort of a more sort of elaborate, as you might expect, sort of reconstruction, really having some multi-scale feature refinement network on top that again is learned end to end here, that we overall get to some 36 point something here PSNR, right? So we came from this 27, right? We get to 36, which is nearly 10 points here, or 9.5 points, whatever. right? And really sort of from the original Wiener convolution, so leveraging sort of the power of neural networks to add on top of this. So now you might argue, right, or might think, so is that any at all competitive with existing methods, right, which don't use this Wiener deconvolution? It just means, let me start with one, qualitative example a bit here. That's sort of Gaussian blur and chippy artifacts. So it's really a mixture of things. That's the blurry image. There's always, a blow up image at the bottom here for the stripes of the zebras. So this is what Wiener deconvolution does. It's not that off, right? It's actually reasonable at this point already. It's not, very good, but it's actually reasonable. And if you look actually at current methods, I would argue sort of, at least visually, they are not much better than quantitatively. If you look at the exact numbers, they are actually better than Wiener deconvolution for the most part, but visually they're not really, there's no qualitative difference really. I'm not sure how well that shows, but actually on my screen, it really doesn't show that much of a qualitative difference. And actually our results here are, I would argue, a lot better, right? It's much, much cleaner, the results you're getting here. And again, using this starting model of a Wiener deconvolution, which is pretty powerful already, right? And you let the network only do the rest anyway, right? So you really don't let the network learn everything, but actually you're doing this by sort of just refining the results or refining what we know about what is a reasonable model to start with, in that case, the Wiener deconvolution model method. And here's the ground truth. And I would argue sort of the ground truth, our results closer to the ground truth than to any of the other results. It really makes a qualitative difference in terms of this performance. And obviously we have quantitative results, and they are actually pretty impressive. I'm just showing two parts of here. One is sort of Gaussian noise across a number of data sets that are standard. So here is our number. Here you always see sort of the improvements. We're getting between 0.5 and 2 points improvements, and this, again, this logarithmic scale is pretty significant considered in that field. And also here for this Martin data set, if you have different noise levels, again, we're getting between 0.8 and 1.6 or so improvements, right, again, in this PSNR scale, which is logarithmic. Right, so here again, some more qualitative results here. So here in the upper left corner, you see the kernel that actually was here now used to generate this blurry image. Again, you have two blowups, the red one, the yellow one here. This is the ground truth. That's what you really want to get, and that's sort of what you're getting right now. And you can judge yourself which of the other methods are really competitive. I would think sort of none of them are really sort of as convincing in terms of the results. Here's another example for real camera shake, where you actually have to estimate, obviously, the blur kernel, right, which we're doing, right, with the standard methods. Here we don't do anything particular, so that's the blur input image. You don't have a ground truth image in that case because they're real image shakes. This is sort of what you're getting out, right, and then here's a pretty blocky version, which is sort of clearly less noise, but blocky. Here of a version where you really have lots of artifacts here, the smearing artifacts, whatnot. So these are difficult, these cases, right, and again, sort of here, it's maybe a little bit less visible, but still, it's, I would argue, really a quite convincing result as such. Okay, so let me just give some concluding remarks here for this part of that talk, right? So we have really this novel feature-based deep Wiener convolution, which is really sort of neuroexplicit as par excellence, in my opinion, right? So we have this explicit modeling for the Wiener deconvolution. You're trying to improve on this by combining with the neural model, right? And you obtain actually a lot better results than you were able to do either alone. We have this multi-scale refining, which is important. It's fully end-to-end trainable, and you get these significant quantitative results. And again, right, there's this downloadable, you can use it, can play with this yourself. And as I get here, the key is it really generalizes well across many settings. So it's not really sort of specific for a particular setting, but actually it is really generalizing right across. Okay, so yes, I have still 10 minutes or so, right? That's fine. Yes. Yeah. Okay, cool. And let me actually talk briefly about this last part. Even though it's a bit older here, it's from 2018. I still think it's a good case where we really have a very explicit, neuro-explicit model that actually helps us, in particular, training with less data. There was a paper at 3DV and actually got a base paper award at that conference, and it's a joint work with Moabed, was the PhD student, Christoph Lostner, Gérard Ponsmal, Peter Gehler, and myself. The task is simple, right, or very easy to explain. You have an SN input, you have a 2D image like this one here. What you want to get out is basically a full 3D pose estimation of the person, right? A really full 3D pose of that person here from that image. And classically, right, or not classically, one of the classic model ways to do this, and that's sort of the explicit modeling part, is you could actually start from a strong body model, right, like the simple model, and then basically, which is, parameterized by pose and shape, and trying to estimate this, right, in order to get really the 3D pose. So that actually is the classic case to think about it, right? And if you're want to use the model-based approaches for this using only 2D key points, right, from in the image, well, then you basically, what you classically do, you do the projection of the respective key points to the image, right? You're looking, you're detecting them in the image, you do the projection, and then you're minimizing sort of the, the difference between the projected points and the measured points or estimated points in the image, right? That's a classic way of doing this. And we all know this optimization, right? And we do these model-based approaches, this explicit modeling can be extremely slow and complicated, right? It's, has many local minima and can be very, very tedious to do this, right? We all have been there, have been doing this in one way or another. So it's very, it really needs sort of careful thinking. Lots of papers have been published and do this well, right? So that is that's a classic way, an explicit modeling case, but it's not sort of, it's not something that really is easy to do, right? In general, at least. Right. So what about sort of just using neural networks? Why not just taking the 2D input, right, of the image and just estimating the 3D output, the pose and the shape directly? Why not doing this? A CNN, right? They're powerful machines. We know that would be great. The trouble is here that it's actually very hard to obtain, reasonably good training data here, right? So actually annotating pose and shape, and people have been doing this, right? Actually, Peter Giller and others have been doing this to really annotating the pose and shape, right, in 2D in the wild images. That actually is pretty tedious and hard. It's error prone. It's actually not that easy. It's definitely not something you really want to do for many, many images. So the question is, can't we do sort of something like a neuro-explicit approach here, right? Which somehow really combines these two things. So the general idea is you're saying, okay, yes, in principle, I want to get from these inputs to the 3D pose and shape. Sure enough, that's what I want, right? But I already said it's hard to obtain. What I really have at abundance is actually 2D key points, right? I have these 2D key points in the wild, take our, data set, the API human pose. There's all kinds of other data sets out there that actually that you can use for 2D key point estimation. So now this is relatively easy to obtain because it's much less error prone. It's still tedious in a way, but it's much less error prone still because it's just 2D annotations is cheaper. So now in order to link this, right, you can now use the simple model basically, project this using those pose estimations if you have them. Use the simple model to render essentially, right, sort of the respective body. Take your key points, right, on that body, right, and project into the image, right, which means now you basically got from input image here, right, to the key points, and in between, you had to sort of, as a bottleneck, if you like, you had to estimate these pose and shape parameters, right? So it sounds like, pretty simple when you look at it, but the key is you can train from obviously these 2D key points here, right, to really obtain eventually this pose and shape parameters in the middle. So let me obviously there's different losses now that one could apply, right? So there's this what we call the latent loss in this pose and shape parameter space. And that actually is, as I said, it's expensive because you don't have many data of this. Maybe some, but you don't have many, and right, and they tend to actually be not that precise. You have the 3D body, the body part in 3D, right? That's the second loss you have, and then you have obviously the 2D loss here in the image space. Okay, so now when we train this right here, just, I'm not going to show this long, but there's this qualitative results that at the top you're getting sort of reasonable results with this, right? And at the bottom, these are literally the worst results we're getting. And yes, sort of in some very unusual poses, you get sort of a bit off here, or sort of the upside down poses tends to be not that good. And also, right, I mean, I'm not going to claim you're the only ones thinking about combining sort of a neural network with this kind of body model. There's quite a bit of work out there. And to me, they're all in one way or another a form of this neuro-explicit modeling way. But let me just, give you some intuition about the numbers. And here we're using sort of Unite the People as one data set and the Human 3.6M as the other data set. And here, if you look, actually, we're getting, so lower is better here for the mean. We're getting roughly the same amount, the same error as other hybrid models, actually, while actually they're actually trained on much more data, actually. But that's the detail. That's not really what I want to talk about. I really want to talk a bit about what is actually here driving the performance, and can we actually reduce the amount of training data? There's really two parts to the game in a way. The one is actually how exactly we're representing the input. I haven't really talked about this here. I don't want to spend much time here on this, but actually the other part is sort of these different losses. Which of those losses are really key to run this thing, right? So really giving best performance. And again, so here, yeah, so this mapping, yeah, let me skip this a bit. So this, maybe I should have taken this out. We have different ways of representations, just a segmentation, a part representation, some body parts, or pose estimation, body parts, right? So which of those are best? And the bottom line, again, I don't want to talk about this long. I can talk about this more. Just show this here. The richer this representation gets, it's not too surprising, the better the performance gets in terms of 3D error. Right? It's not too surprising, but already sort of, some parts, here 12 parts, 3 parts, they're all giving you already reasonable results. So the representation plays a role, but that's not my main point. And on 3.6M, that's the same game. What I really want to talk about here is a bit more which kind of supervision I need. And again, as I said, right, this latent representation or latent supervision actually is costly. So how much is that important? So let me first show you a comparison here now. So now here we're looking at 3 types of errors. The one is actually sort of 2D joint. That's, percent of correct key points. So here, the higher, the better, right? Then the 3D rotations really of the, the human body. And then the 3D joint position in 3D space. If I only use 2D, right? So I'm reasonable on this, PCK, which is sort of on the 2D evaluation. That's where this works well, right? So on the other one, sort of here, this is sort of 1.9 in quaternions is actually not good, and also 189 millimeters is really not good, right? That really is far off. So now if I have the 3D annotation, so the 3D annotation is on the points in 3D, as you would expect, this one goes down here quite a bit. Actually, you can half here the error, right? Or actually more than half the error, right? Sort of the PCK stays about the same, but the quaternions, again, the rotation is not good, right? So it actually does not really help here much, right? It's basically the same. So now if I take the latent, so the pose and shape, supervision, right? This actually stays about the same as here, right? So now here I get this really drop in the improvement in performance, right? Here lower is better, really a strong improvement in performance, right? And also here in terms of the 2D joints, right? It's not much lost here really, right? So only this actually is not is doing in a way the best, right? So really this, which is sort of the unfortunate thing, right? I really need that. What's most expensive is the one that actually gives the best performance. So if do everything together, right? So I'm doing good across the board. So now, so that works well, but it's exactly that kind of very expensive supervision that actually plays the game. But now we made another experiment by trying to understand how much of this latent pose and shape supervision do I need, right? Here I'm looking now at the 3D error in millimeters. So if I don't have any, I'm having this close to 200 millimeters error, right? Which is really bad. If I annotate 1%, this really is very little, like 1% of the images with these pose and shape parameters, right? I'm already dropping this by a significant amount. If I have 5%, I can slightly improve, but the rest is actually not necessary really for annotation here. That's a bit surprising, right? So only having very little data, right, that actually gives you the supervision for the latent space is actually sufficient to make the entire pipeline actually good also in 3D position errors, right? So that actually is good news, right? Because having a pipeline, again, a neuroexplicit model where there is a simple model, sorry, really body shape model, like simple model in our case, in the middle as an explicit model helps you basically to reduce the amount of training data dramatically, right? You're talking, 5 or 1%, whatever accuracy you want at the end, but it really is allowing you to really reduce the amount of data a lot that is required even for 3D estimation. Okay, so let me sum up here, and then obviously I'm open here for questions. So still, I said, why these neuro-explicit models, right? I really made these 3 points: interpretability, generalization, and reduction of, required data. And I think sort of I hope I showed you a bit, right? Sort of that in the 3 cases, at least for the coda nets, we really were able to get some interpretation out that actually is, by design inherent in the network, right? By still preserving at least sort of reasonable performance at the moment. And yes, we're working on better models on this front. Also generalization, right? This deep Wiener deconvolution, combining a deeper Wiener convolution with deep learning, really allowed us to go, generalize across a wide range of settings. And then here, sort of the 3D model in the very last part of the talk allowed to reduce the amount of 3D supervision here. I mean, I still use, and I can say this, I still use sort of full amount of 2D supervision, but again, this is much cheaper, right, to obtain. It's more precise. But the reduction of the 3D, the amount of 3D annotations really was reduced by a lot. With that, I'll thank you very much for your attention. I'm very open for questions. Any you would have. Thanks.
Thank you, Bernt. Thank you for this very inspiring talk and this amazing overview of some of the research in your team. Very impressive. I think we can have some questions, so we'll have live questions and possibly also questions from YouTube. I would like to start with one question from my side while there's no live questions yet. So please, if the live audience, if you have a question, just type Q in the chat so we can call you. And I wanted to start with a question on your first part, Bernt. You mentioned that you applied it so far to CIFAR 10 and tiny image, and you said there is a challenge of getting it working on larger image. Can you elaborate a little bit? What is the challenge? Is it a runtime challenge, and where does it come from?
Yeah, maybe I just go to one slide here. Because I haven't given you some of the details. So the way we're doing this really, I mean, what we call this dynamic alignment unit, right? So we're getting this as a set of the input dependent mapping, right, to the input dependent linear transformation. And the way we get this, actually, we're having here sort of an A times B. So that actually is, it's not a single matrix. It is an A times B to have still not a full rank thing that we need, but you still have to basically have sort of relatively large matrices here. And then that means to have actually a relatively large matrices to deal with, right? And we have streamlined this by now, right, to how to handle this, but that's right. So that's sort of, there is sort of a relatively expensive operation at the moment that we can, as I said, we have streamlined in the meantime, which actually that will be published. And I think we have actually completely new version that actually gets completely rid of this, that we're going to talk about later this year, most likely. But there is, which still preserves the same, how to say, the same perform. To be honest, I mean, we have been actually training it on ImageNet 100, so we can do this full image resolution. It's just sort of, it's right now it was still relatively slow in its in its training procedure, right? So that this is what you haven't really talked about. And I mentioned it, but that's sort of a bit the downside of the current version of this.
Coming to the second part, there is a question from our YouTube audience, in particular from Bartek Stanovsky, who is asking whether your method can be used to get license plate numbers acquired from blurry, moving, low-resolution video.
In principle, yes. I mean, it's a classic deblurring task, right? So in principle, I mean, if you have a moving camera, right? I mean, as I said, it's a non-blind deblurring method at the moment. So we're estimating the kernel, right, with sort of off-the-shelf methods. We have just not used anything specific, right? So we even use it off the shelf as it's downloadable from the internet, right? So in that sense, as soon as you have a reasonable estimate of the kernel, right, you can apply the methods essentially out of the box.
Mm-hmm. And I think one of the key kind of innovations in the second part of your presentation was to use this Wiener degradation model combined with deep learning based approaches, right? What kind of surprised me there is the first example you showed was the zebra example. And as you mentioned, there is blurring, but there's also JPEG artifacts. Now, I'm pretty sure Wiener in 1949 did not model JPEG artifacts. At least I don't think JPEG is that old. Would it be possible to generalize your approach to include a modeling of the real degradation process? You seem to be aware of what the degradation process is. So sure. I would guess the better you can model it, the more performance you should get.
So I mean, yes, I mean, you're exactly right. So I mean, that would be really an interesting way of extending sort of the this classic explicit model of Wiener deconvolution to these kind of artifacts. I fully agree. To be honest, we really took then sort of the the lazy deep learning approach here, right? We basically gave it a sufficient number of sort of artifacted images, right, and then it would pick it up itself, right? So I think, yeah, I mean, it still has this. I mean, it has specific blurry artifacts, as you exactly say, right? You could certainly improve on this, but that's actually a bit of where I think there's a bit of generalization. Really, the argument goes, right? So you really can train it on certain things. It really generalizes. Actually, I haven't really made this point strongly, but you can train on one particular, subset of noises and actually generalizes to other sets of noises or even artifacts, right? So it seems to be pretty robust in this respect. Again, I'm thinking of this Wiener deconvolution to be of a bottleneck, right, as it is in this. In the 3D modeling and the simple model in the last part of the talk, right? It's sort of a bit of a bottleneck which rectifies and regularizes what the neural network actually has even at its disposal to work with, right?
Thank you. Any other questions? Maybe, so Lucas says no more questions on YouTube. I have one more though, for your last part, the third part. You mentioned in the body fitting, the classical approach is to minimize the reprojection error between these key points and the projection of key points. Now, the key problem there, I guess, is that if you have a small reprojection error, it doesn't imply that you have a small pose error, right? This is the key challenge. Is that the reason why this latent space is so vital, and having at least some sparse ground truth on the latent space for training?
Yes, this is also my intuition, exactly. So it's my intuition also that you're basically, I mean, the way this is trained, actually, that is, I mean, I'm saying we're using less data, but actually the losses are equally weighted, right? So the few training samples are equally important than sort of the ones that are in the 2D space, right? Because it's trained jointly, right? At the end, they're equally important, which means all of the representations that are learned intermediately, right, have to go through this, right? It's basically, again, you know that the simple model can deal with the pose and shape parameters eventually, right? So if you basically getting them right, with these, even few examples, right, they're going to be gotten right also with the rest of the examples. So really, I mean, since it's still a heavy sort of loss there, even though it's only a few images, it still goes through there. And yes, and it seems that actually this actually seems very vital, as you said, right? And it seems, yes, there seems to be some strong prior now learned, right? What the poses are, right? What rotations make sense, right? Which is essentially what the simple model gives us back, right?
But for this approach, you do require the simple model as part of
indeed,
the
right?
approach.
Yes.
Is there a way to get around the simple model, because it's a fairly heavy model, right? And
no, you're right. I mean, I think there's nothing specific about the simple model here at all, right? I mean, you could use some other model, right? Whatever you have, you do spatial puzzles. You could also think probably of something simpler. I mean, you could even think of, actually, that's not something where we went, but you could also think of something that is a very simple stick figure model in principle, right? That actually is even, that might be even easier to annotate in the first place in the image domain, right? Where you don't even have a body pose, because there's nothing we use. We don't use the body shape here really, right? At the end, right? For this regularization. I mean, at the end, we wanted to have it, right? And that's why we had it. But in principle, if you're only interested in the skeleton pose, whatnot, right? You really could use another model in there, right? That actually would give you most likely the exact same boost, right? In terms of being a bottleneck for this. Yes, I agree.
Now, this last approach, it's a single image-based approach, right?
Exactly. Yes, that's right.
Have you looked into extending this to video, fitting, actually to video?
No, we haven't really done this, but it would be relatively
one
straightforward.
solution would
right?
be obviously frame by frame, but
Sure.
I guess there's more sophisticated solutions.
No, I mean, we haven't really. I mean, this was sort of towards the end, I guess, of this piece of work. No, I mean, but you're right. I mean, it could be obviously extended, right? And but you also could have an additional, explicit modeling of the motion that is possible and whatnot, right? So, I mean, it's quite easy to imagine that you do this, right? Not just, as we said, frame by frame, but really sort of having an explicit model of altered motion on top, right? That actually could be used as an additional constraint or bottleneck, as I like to call it.
Excellent. Is there any last question? No? Okay. Bernt, thank you so much for being with us today and for this great presentation and lively discussion. Thank you so much. And that concludes our presentation today. Thank you.
Thank you. So.